In the previous video, I showed you how to recognize that what you had was a trig substitution problem. You're looking for square root signs, and underneath the square root signs, you're looking for one of these three forms: a number minus x squared, a number plus x squared, or x squared minus a number. If you come down here to this problem, here's your square root sign, and you see 2x squared plus 8. It's not quite what we see here, but I think we can algebraically manipulate it so that it fits this form, and then we'll end up doing this substitution. So how does that work? Well, we don't want 2x squared plus 8. We want x squared plus some number. So there's a little bit of algebraic work to do here before we even get to part 1. I don't know, maybe part 0. What I have is the square root of 2x squared plus 8. But I can't have this coefficient. It can't be 2x squared plus 8. It has to be x squared plus some number. So what I'm going to do is I'm going to factor out a 2. So I got x squared plus 4. Cool, but it still doesn't quite fit the form because of this 2. Right, but what I can do when I have the square root of a product, 2 times x squared plus 4, is I can make it the square root of the 2 times the square root of x squared plus 4. You cannot distribute square roots over multiple terms. I can't make this the square root of x squared plus the square root of 4, but you can distribute the square roots to different factors. I have 2 times x squared plus 4 underneath the radical, and I can rewrite that as the square root of 2 times the square root of x squared plus 4. With that work, I can take my original integral here and rewrite it as 1 divided by x squared times the square root of 2 times the square root of x squared plus 4 dx. This might look complicated, but remember that this square root of 2 is just a constant. You can think about this as 1 over the square root of 2 times 1 over x squared square root of x squared plus 4. I can pull constant multiples out in front of the integral symbol, so I got 1 over root 2 out in front, and then my integral is just 1 over x squared times the square root of x squared plus 4. All of a sudden, it looks like a really good fit for what I have written right here. The square root of some number plus x squared. I guess if you want, you could rewrite this as 4 plus x squared underneath the square root sign, because addition is commutative. And recognize that playing the role of the a in this expression is the number 2. So my trig substitution is going to be x is equal to 2 tangent of theta. Or technically, divide both sides by 2 and take the arctangent of both sides. Theta is equal to the arctangent of x over 2. Remember, these two things are equivalent. This is the substitution that feels more like a u substitution, but this is the form that we want to take the derivative of, because the derivative of arctangent is really ugly. Take the derivative, we got dx is equal to 2 times the derivative of tangent is secant squared. So I got secant squared theta d theta. I have an expression for x and an expression for d theta, so I can plug them into this expression. I get 1 over root 2 times the integral of 1 over, and then instead of writing x squared, I'll write 2 tangent of theta squared. And then instead of writing the square root of x squared plus 4, I'll write the square root of 2 tangent of theta squared plus 4. All my x's have been changed to expressions involving thetas. Now I have to do the same thing with the dx. dx is 2 secant squared theta d theta. This huge mess of an expression might not seem like an improvement of the original problem, but it really is, because I'll be able to simplify underneath the radical here to change these two terms into one term and cancel out this square root. You might not see it yet, and that's okay. I'll take this 2 secant squared theta d theta and write that up on the top here. 2 tangent of theta squared is the same as 4 tangent squared theta. So I get that expression outside of the radical, and then I also get that expression inside of the radical, 4 tangent squared theta, and then I got this plus 4. Note that this constant term is 4, and this coefficient is 4. How convenient. I can factor out a 4 from each of these terms. I guess while I'm here, I might as well reduce this 2 and this 4 also. So I got 1 over the square root of 2 times the integral of 1 secant squared theta divided by 2 tangent squared theta times the square root of 4 times tangent squared theta plus 1. I write my d theta at the end, and I'm in pretty good shape. Why am I in good shape? I still have 2 terms here underneath the radical. Yeah, but tangent squared theta plus 1 can be rewritten using our Pythagorean identity. You might not have memorized that tangent squared theta plus 1 is equal to secant squared theta, but really you won't need to have that memorized, because it's always going to be the same. If your trig substitution was to involve a tangent, then you'll end up with tangent squared theta plus 1 underneath the radical. And if I go all the way back up here to where I originally wrote my Pythagorean identity, and I divide each of these three terms by cosine squared theta, I get sine squared over cosine squared, which is tangent squared theta. I get cosine squared over cosine squared, which is just 1, and I get 1 over cosine squared theta, which is secant squared theta. Tangent squared theta plus 1 is equal to secant squared theta, so I can replace these parentheses here with a single term. A little housekeeping while I'm here, I might as well pull this 2 out in front of the radical. So I got 1 over 2 root 2 out in front of the radical now. I got secant squared theta up on the top. Down on the bottom, I got tangent squared theta out on the outside still. And then underneath the radical, I got 4 times, instead of tangent squared theta plus 1, I got secant squared theta d theta. I have a single term underneath the radical. I can cancel out the square root sign and be done with part 1. The square root of 4 times secant squared theta is 2 secant of theta. Technically in the absolute value symbols, but you don't have to worry about that. I'll take the 2 and bring it out in front. So I got 1 over 4 root 2 out in front now. And then the secant that results from here will cancel out with one of the secants up here. And I'll get secant of theta divided by tangent squared theta d theta. We've gotten rid of the square root sign. We're done with part 1. That brings us to part 2. We've done all this work, but we still have this integral symbol here. We haven't done the calculus yet. We've just done a bunch of really challenging trig. To do the calculus, we got to integrate secant of theta divided by tangent squared theta. So what's the antiderivative of secant of theta divided by tangent squared theta? I don't know. It's not obvious. You might try to do some sort of u substitution here, but I don't think anything works out too nicely. When you're in situations like this, often a good strategy is to rewrite your trig expression in terms of sines and cosines. So instead of writing secant of theta, I'll write 1 over cosine of theta. And instead of writing tangent squared theta, I'll write sine squared theta divided by cosine squared theta. Maybe that will give us a form that's easier to integrate. Let's see what happens. I got a fraction divided by a fraction. So I divide the fractions by multiplying by the reciprocal of the denominator. In other words, I take this one and flip it upside down. So I got 1 over cosine of theta, what used to be on the top, times, instead of divided by, this thing upside down, cosine squared theta divided by sine squared theta. Does that help any? Well, I can cancel out this cosine and one of these cosines. So I get 1 over 4 root 2 times the square root of cosine of theta divided by sine squared theta. Can you get it from here? I think this is something that you can integrate. Maybe you'd want to use a u substitution. When you're using a u substitution, you're looking for something that u can be equal to, so that the derivative of that something shows up in that expression. If we choose u to be equal to sine of theta, then du would be equal to cosine of theta d theta. That would be awesome because I got cosine theta d theta right here. So with this substitution, this integral becomes 1 divided by 4 root 2 times the integral of the cosine theta d theta all change into a du. So all I'm left with is 1 over sine squared theta, but sine of theta is my u, so I get 1 over u squared. In other words, u to the negative 2 power. Oh, that's easy to integrate. The antiderivative of u to the negative 2 power, using the power rule, I add 1 to the exponent, and then I divide by that new exponent. I tack on my plus c, and my integral symbol is done. I can clean this up a little bit if I want. 1 divided by negative 1 is really just negative 1, and negative 1 times 1 over 4 root 2 is negative 1 over 4 root 2. Instead of writing u to the negative 1 power, let's change my u's back into sines. So I got sine of theta to the negative 1 power. In other words, 1 over sine of theta. In other words, cosecant of theta. I'm done with my integration. I'm done with part 2. All that's left to do is change my variables back and simplify. To change my variables back, I just have the 1 theta floating around. Recall that our original trig substitution was that theta is equal to the arctangent of x over 2. So since theta is the arctangent of x over 2, this answer is really negative 1 over 4 root 2 times the cosecant of the arctangent of x over 2 plus c. This is a great answer. I like this answer a lot. It's equivalent to the correct answer. But every book and every teacher you ever run into is going to tell you not to leave your answer this way. You shouldn't leave inverse trig functions nested inside of trig functions. You should instead simplify. So maybe off to the side here, I'm going to simplify the cosecant of the arctangent of x over 2. How am I going to simplify that? Well, I'm going to choose theta to be equal to the inverse trig function, arctangent of x over 2. Because if theta is arctangent of x over 2, then the tangent of theta is equal to x over 2. And if the tangent of theta is equal to x over 2, I can draw a right triangle. Using SOHCAHTOA, I know that tangent gives me the length of the opposite side divided by the adjacent side. So if I put theta down here in my picture, here's opposite, here's adjacent. If I know two sides of a right triangle, I really know all three sides because a squared plus b squared equals c squared. So 2 squared plus x squared equals what I should write right here, squared. So what I should write right here is the square root of 2 squared plus x squared. In other words, the square root of 4 plus x squared. With this triangle, I'm able to simplify this expression, because remember, this expression might say the cosecant of arctangent of x over 2, but the arctangent of x over 2 is just theta. So really, this expression is saying, what's the cosecant of theta? I could figure out the cosecant of theta just by looking at this picture. I know that cosecant is the reciprocal of sine, and using SOHCAHTOA, I know sine is opposite over hypotenuse. Therefore, cosecant is hypotenuse divided by opposite. The cosecant of theta is equal to the square root of 4 plus x squared divided by x. The cosecant of the arctangent of x over 2 is the exact same as the square root of 4 plus x squared over x. This is just a simplified version of this expression. But using the simplified version of this expression, I can rewrite this answer over here in a prettier form. My final answer would be -1 over 4 root 2 times, instead of the cosecant of the arctangent of x over 2 plus c, it'll be the square root of 4 plus x squared over x. And then if you remember, plus c. This looks a little bit weird. I can't help myself, so I'm going to clean this up a little bit. I'm going to make it the negative of 4 plus x squared divided by 4 root 2 times x plus c, but that's just for aesthetic purposes. What's written here is identical to what's written over here. Either one could be your final answer. And if you're getting these final answers, you should be really proud of yourself. This is arguably the most challenging thing you'll ever do in a Calc 2 class. Before ending this video, the one comment that I want to make is this part 0 that I had to do here wasn't specific to this second trig substitution. Anytime you have a coefficient in front of your x, whether it's here, here, or here, you have to do a step similar to what we did here, where you factor things out so that your coefficient becomes a 1. I just waited until now to show you that little trick because there was plenty of other stuff to learn in the previous videos. We'll do one more example in the next video, and then you will have seen all the different types of examples that you can do with trig subs.